Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Chris Jackson, and Fred was talking to me about stress. Or was there something else in addition to stress?
Yeah, and strength.
Strength. Okay.
Yeah, stress, strength calculation. Remember those things?
Yes.
Well, actually, it was a question that came in. Asif, A-S-I-F, if I'm pronouncing that correctly. Asif sent a question over and was asked to do some calculations to estimate expected failure rate or reliability type figures using a situation. They didn't provide the details of what product it was or what kind of calculation it was, but it was a mechanical engineer said, well, I can give you the maximum stress and I can give you the maximum strength. And I'm like, okay. and just single points. That's all I got. And I don't know whether they were from specs or from engineering judgment or wherever they came from. And so the question was basically, so what do I do now? And had a disdain for using, I think it's, what was the name of the database that he referenced here? Let's see. No, he didn't mention it. But for mechanical parts, there's a handbook that lists all kinds of failure rate type stuff, NFPD or something like that. I don't remember the name of it. But he didn't want to go to there because he didn't know where that data came from or if it applied to their product or environment or anything else. And so I was kind of asking the right questions, but what do I do? If all I have is a drawing that has maybe a spec or a tolerance, essentially, this is how strong this could be. And a set of, here's what the environmental stress that we're designing for, that's its number. And so the question is, what do I do? How do I make progress with this? So I thought I'd hit you with that one because I'm quite sure you've seen something like this before.
Yeah, and you can't answer that question without having more information. And that doesn't mean that as a reliability engineer, you go too hard, can't answer it. You might need to be clever with how you generate additional information, which can come through things like assumptions and expert judgments and even some basic logical stuff, including, let's call it envelope scenarios, where you say, well, in terms of the variation of strength, the worst case scenario could be this. And the stresses, well, the worst case scenario could be this. In addition, not just in terms of the max strength and max stress, but how that stress is distributed, because those maximum minimum values are just analogous to limits.
Right. And it doesn't give you the mean or a variance term. So
right.
So my first piece of advice was, well, head to the lab, go make some measurements, figure out, or maybe, if you don't have a bunch of systems out there that you can go measure it. And so let's say, just as hypothetically, that it's a flange, for example, the tolerancing of that flange to the manufacturer says, what size it could be and what radiuses and all these other things that are specified. Well, all of those could vary. Well, what is your actual variation? And then go back to your CAD system and say, finite element, what's my strength, relative strength, if it's a millimeter difference in thickness? Or is it more material property? What's the variation, a relationship between some manufacturing step for your material and its eventual tensile strength, for example, or whatever. And maybe you'll find some papers on it or some somebody studied this already or go, my favorite part is go to the lab and break it, go measure it. It's always a lot of fun. And then the stress side of it, same thing, is instrument a bunch of them up and get people to stand on it or load it up or put a forklift load on it or, whatever. Just actually go get measurements and get something. So I was surprised that your first thought was, well, use expert judgment, or I think was another equal. I wouldn't say equally valid, but as valid. It's just different set of assumptions because I have measurement error and I've got all these other problems. But I like the logical approach. Like, well, how weak or how strong could it be? And it sets a boundary, and then we can assume a distribution in the middle of it.
I just like when I mean the problem summary comes down to just not having enough information. So when I start explaining what information can look like, of course it could be from your own test data. I always like starting with the stuff that most people tend to discard from the very start. But I agree with you. You can no reason why you can't go to your own testing. The other thing is, you could ask, I know this goes against the context of the problem where you're just given a number, but for example, let's just say it's minimum strength. Unlikely to be maximum strength of a component. It's more likely to be minimum strength. Mm-hmm. A vendor is not going to probably say, this will be no weaker than X.
Yeah, that makes sense. Yeah.
Then you could ask the vendor, why do you think this? Why do you think this is the weakest, the minimum strength of your component? You might be surprised. They might say, well, we do SPC and PCA or what have you, and that's our lower specification limit, and we maintain a capability index of 1.7, which exceeds our. And all of a sudden, you go,
got all kinds of data.
yeah. You go, well, if you got that information, you can very easily work out the probability that a component's going to be weaker than that minimum value. So just asking, you might be surprised what you can get from your vendor. That number had to come from somewhere. If it came from...
Not always, Chris, in my experience.
Yeah. Well, it had to come from somewhere. It could have been from a rigorous analysis, or it could have been from a lunchtime meeting on a Friday where people asked, well, what do you think? So it came from somewhere. That place could be more reputable than others. But
well, I mean, I've mentioned this story a number of times, but I was sent to a fan manufacturer for electronic component size fans, and I asked where their reliability figure came from, and they said, well, everybody else advertises this number, so we use the same number. I mean, it was literally from the general manager saying, oh, that we just use that because everybody else puts it on our data sheet. It has nothing to do with how long they last. It's like, okay.
Yeah, you already lost before you started.
And they were the best. But, in our internal data of using different vendors and tracking fan failures, which was one of the higher Pareto issues across the company, this vendor was the best. They performed better than anybody else. Their products lasted better, moved more air longer, that kind of thing.
Good Lord.
And we're trying to figure out what did they do different. And basically it was counterintuitive for me from a reliability point of view, is they completely ignored reliability and just designed products, and it just turned out to be pretty good.
Yeah. Well, it might be a little bit counterintuitive unless it was an industry standard, just to use an industry standard reliability figure.
It was. I think it was the marketing thing, and they didn't think anything more of it, and it's on the data sheet. Everybody else has it on their data sheet, so we'll just use what everybody else is, because apparently the market expects that kind of number, and okay, off we go. But anyway, that's the exception. Vast majority of the time, you will get reliability, but it'll be something. Right. But this poor folk, Asif is, looking at, I don't want to just make up a number. I think there's a Dilbert cartoon about that. It says, well, if I have no information and not a clear question, I could just give you any answer and you'll be happy with that. And his boss goes, yeah, pretty much.
Yeah, I mean, but again, you should never just assume the vendor has nothing. I mean, you might be cynical after years of dealing with recalcitrant vendors, but not all vendors are recalcitrant. So
no, that's true. I agree. That's a good. I didn't think of that. Ask your material suppliers or manufacturings or whoever. Get some more info, and if nothing else, you can get some more experienced background or expert knowledge kind of thing to say, well, here's a range that you could expect.
Right. Right. And then, I mean, you can also use that conversation on the phone to work out whether you trust that organization. Because if they simply say, well, we've been in this business for X hundred years and, we've got reams of data analysis and this, that, and the other. And you say, okay, what is that data analysis? It's just data analysis. It's really robust. What is it? Robust data analysis. You go, okay,
Right,
so
yeah.
you don't have any idea.
We used Excel once, yeah, until or something like that. No, I hear you, but I mean that's a great idea. Especially if they're, trying to create a stable, consistent product, they probably do use process capability in SPC, and if they do that in a meaningful, that's what's the word that you have is tranche. They have a whole pile of data.
Tranche of data.
Yeah, tranche of data.
but that would be real. If you do an SPC and PCA, that's actually going to be a really massive and useful data set.
Oh, yeah.
That could hypothetically be given to you for free.
Yep. Now, how about the other side, though? Because the vendor is less likely to know what range of stresses that your shaped piece of metal is going to expect to withstand, for example.
Yeah.
So what do you do there? What would be because I thought, if you've got willing customers and the marketing team doesn't allows engineers to talk to customers, then you could go make measurements or replicate the range of measurements, or I don't know, or assume worst case and put a distribution on it. But I'm more fuzzy about how do you go about getting the environmental side, the stress side that you're expecting to see.
Well, the other thing is that let's just say you've gone through step one and just say you got some meaningful information from your vendor. And let's just say that meaningful information allows you to create the PDF curve of strength, like the strength curve.
Right.
You might be able to look at that straight away and say, hang on, the maximum stress level given to me is actually 14 standard deviations below the mean. So you might need, that's all you might need to do is say, hey, team, I just analysed the strength and here's the best guess and this is reasonable, even with some, allowances for inaccuracies.
Yeah.
But this is so far above the figure you told me was a maximum stress level that we can be reasonably confident that it's going to be A-OK. Of course, we don't have a question here. The question could be, is this okay? Or the question could be, what will be the failure rate implied by this stress strength interference curve? Or, but if the question is, are we okay? Then you could just be that simple.
Well, that issue I have with that is thinking through a problem like this is that that would be wonderful that you're orders of magnitude away from where you expect stress to be, and you have reasonable expectation of this is the upper stress that you're going to see, factoring in solar flares and earthquakes and everything else. You're like, we're minuscule chance that this.
Where is this component being used? It's going to be simultaneously hit by an earthquake and a solar flare. Well,
it's California. Yesterday was a big solar flare storm, apparently. Not enough that it affected. Although I was on a cell phone with somebody and they kept fading out, and for whatever, and she was like, for whatever reason, today's cell coverage here is really bad. So I attributed it to the solar flare storm, the solar storm. But she said, no, it's like that all the time. The more important the call, the less often that we got coverage. So. But there's three scenarios. I look at it is that there's one where it's obvious you're so far away, it's not a problem at all. And then the engineer is going to say, oh, great, I'm going to shave off, 4 pounds of metal off of this thing and make it a lot weaker because I got room. Or the marketing guys are going to say, oh, you can put 10 times the load on this thing and you'll be fine. And, it's like, hold on, guys, hold on. Having a big margin does not mean you get free lunch, kind of thing. The other scenario is that, you go through the strength and your strongest end of the strength curve is below your stress, is the stress is going to dominate is what I'm trying to say. And then you're in big trouble. Yeah, this isn't going to work, guys. And let's go to the lab and just break one. It makes it easy and just show them. But the worst scenario is where you're in the middle and it's like, it overlaps. It could be overlapping 1%. It could be overlapping 10%. It's just a guess. But there's no clear picture that it's really good or it's really bad.
That said, it's been my experience, you tend to find extreme interpretations rather than the sort of textbook picture. I tend to find scenarios where the stress clearly exceeds the strength, which is bad, or the scenarios where the strength clearly exceeds the stress, which is good.
Mm-hmm.
I find that, especially organisations that haven't thought a lot about it, the chances that the design stress happens to be in the ballpark as the design strength for organisations who haven't really thought about it too hard is relatively small. So a lot of the time you find it.
No, I have to disagree on that one, Chris. I've run into engineers that don't understand this concept of stress strength or derating at all. And one example is from electronics, is they said, well, I need a pump that moves, so much pressure. And they went to the catalog, they found a pump, and he says, oh, it's cheaper if I get one that their rated ability is what we need. And they had no margin at all.
Mm-hmm.
And half their products failed.
But that's my point. That's what I'm saying. I find that organisations who don't do this well, from my experience, they tend to be one extreme or the other. They tend to have a horrible stress strength curve scenario where the stress really exceeds the strength.
Yep.
Or they just luckily have a strength which greatly exceeds the stress.
Yeah. Yeah.
That's what I'm saying.
Yeah. I've seen cases in both, and yet to me, it's like you want to be clear about it, and getting a good estimate of the variances is about the only way you can really understand, because, if the stress really could go from like no load whatsoever to a negative load, and I actually ran into that once where it was, instead of supporting a weight or a mass, the mass that was on this flange, for example, was pulling on it. And the designer went, no, well, that's not supposed to happen. And I was, well, then you explain why this flange is bent that way. Negative stress he just didn't comprehend that one at all. And it wasn't designed for that. It was kind of weird. But anyway, I run into it in not just stress strength calculations, but any experiment. If I run the experiment and I don't have enough samples, it's very likely I'll get a non-conclusive answer. And so thinking through this problem, I was like, well, what are the scenarios that could happen? And if I have scant information, what's the probability of getting a non-committal answer? And it goes up dramatically when you don't have a whole lot of anything. And so I was focusing on just, well, what are the variances? What are the variability of each of these two curves? Not necessarily what their distribution is, but how much could they vary? And there I can say, all right, if that's a key piece of information to know whether these two PDFs overlap at all, or to any significant extent. But just having 2 point estimates or 2 specs doesn't give me any information about the variability.
Right. And I mean, I often use if someone gives me like, this is an absolute upper limit of something.
Mm-hmm.
You go, do you know much about it? No. But this is the absolute upper limit. Then one approach is simply going, okay, I'm going to assume the mean is half that. So if the upper limit is 10, I'm going to assume the mean is half that, and have maybe assume that the upper limit is 2 standard deviations or 3 standard deviations above the mean, because that actually is quite a spread out.
That's pretty spread out, and that's pretty conservative too.
Right. And you need to truncate it a little bit too, because it's so spread out it would go below zero. But
which can happen.
Which can happen. Well, that might be something you need to consider as well. But if you can't have a stress that goes below zero, which in some cases is true, then you truncate or use a log normal. But either way, use some basic. All right, what's the most conservative way of including a lot of variation, reasonable variation? You don't want to create work for yourself unnecessarily.
Well, you see that in some studies, they say the most conservative is a uniform distribution. Just spread it out all the way across, so the tails, the extremes get weighted heavier.
But that's not based on any, I mean, that's just a premise that people use.
Yeah, that's just I don't know if it's skewed or normal or whatever the shape of this distribution of a PDF is. So I'll assume it's uniform,
But that's actually throwing information away, because if you have a typical value of anything, then you know that the PDF shape is going to have...
It's going to have a peak. It's going to have a point.
It's going to have a peak, yeah. So it's going to be a log normal or a Weibull with a high shape parameter or a normal. So using the uniform distribution, I feel like a lot of people think, oh, that's the most conservative approach. But also, the uniform distribution also implies hard upper and lower limits. So you need to say, all right, it goes from 0 to 20, but that means that it will never, ever go above 20, whereas that's not a constraint of the normal distribution, or the log normal distribution. Right. It will still have a finite chance of it going above whatever limit you put on it, which I prefer.
Yeah, no, that's a good point. Yeah, no, that sounds good.
The other thing, too, is what's the stress? I mean, if the stress is, for example, voltage from a regulated power supply that you've got in your system, then there's not going to be a lot of variance from that stress. If it's just a 3-volt power supply, that's not going to have the same peaks and troughs as...
Well, it depends on where you plug it in. You might get a 3,000, 10 millisecond spike in there, a 3,000 volt spike coming through.
But that's a different problem, though, which is, I concur with what you're saying. You can have dirty power supplies with that, initial spike.
Yeah. No, there's all kinds of sources of variation. And the hard part is, but you're right, if it's a 3-volt supply from a battery, for example, it's going to fade. And that's about the biggest variation you're going to get. It's going to go from 3 volts to 2.5, and then your system says, hey, I'm tired.
Which usually means that, that's bad news in terms of your system doing what it's supposed to do, but it's also less stress. Yeah. So either way, you make some reasonable assumptions about the variation of the maximum stress from a battery, which is a good example. It's not going to, if the maximum stress is 3 volts, it's not going to be too much higher than that ever. Whereas if the stresses are associated with the braking of a vehicle,
now you got to consider load and angle of the road and speed of braking and all kinds of other forces come into play on that one. That
alcohol
gets tricky.
Consumption, all those things. Yeah. That's where variation is going to be.
How dependent the driver is on their horn instead of the brakes, and all kinds of
road conditions, seasons.
Not to mention material properties of the braking materials.
Right.
It's okay. Yeah, we could get deep dive into that one, and then we'd never get on a truck or an airplane or a bus again.
Right. But I think my point is that if the stress is, for example, a voltage from a battery versus braking stresses associated with a vehicle, you clearly know one is going to have way more variation than the other.
Yeah.
And so don't introduce variation to be conservative unnecessarily. If you just ask, well, where does the stress come from? You can perhaps say, oh, okay, I don't need to have 3 standard deviations which go to the moon on this stress.
Yeah, and that's a good point. I didn't even think of that one at all. What's the magnitude of this calculation? Is this life-saving, or is this super dangerous, or is this one of many pieces in here and we've never had issues with it, and it's not a novel new design, and we're just trying to get a figure of merit here, or is it catastrophic? So yeah, there's a lot of ways to go at this thing. But anyway, that was one of the many regular, frequent, what's the right word here, Chris, that we receive questions on a regular basis. Not
hot topic?
I don't know. But anyway, we received this question, made a nice podcast discussion and a couple different options, and learned a little bit as I went along here. I appreciate the insight on the uniform distribution, for example. And so hopefully you as the listener picked up a couple of things out of this. It is, and it's one of those things that if you've got a question, ask it, because other people may well have a similar question or will run into a similar situation. So it's a way to share the knowledge and do all those other good stuff. Plus it gives Chris and I and the other hosts of the show something to talk about. So head over to accendoreliability.com/go/SOR, and you can find a couple of different ways to leave us a message, or Chris and I and the rest of the hosts of the show are available through LinkedIn or through our about pages on the site. So plenty of ways for you to get some comments or questions over to us. And we certainly like to see that. We're actually, I think, Chris, at the lower end of our stress limit on the number of questions we get, because we seem to be able to keep up with it pretty well.
So the stress is low, strength is high.
Well, I didn't say anything about strengths, so we'll have to come
Well,
back and talk about that some other day.
It's all relative, isn't it?
Yeah, we got 4 more, or we do 2 a week, so we've got 5 more days we could do podcasts, so we got plenty of margin here.
Fair enough.
Yeah, we're good. All right, well, thanks, Chris. Thanks for your insights on this one, and we'll look forward to some more questions, see what comes around.
Looking forward to that one as well.
All right, thanks, Chris. Talk to you soon.
Bye.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.